Alright everybody, this is a video again about another one of my friend Isaac's blog posts. This one's going to be about gradient descent, which is used in linear regression. And it's actually used kind of in almost every model that you'll touch on in some way, shape, or form. The goal of it is basically, if you have 2 points and you're trying to draw a line between them, the question is, how does your computer arrive at that line? And so you think of it kind of like how you perform something like sum of squares. To touch on this, Isaac goes into detail in text, but I think most of his benefit is actually through the diagrams that he presents. So he starts it off basically with this diagram here. You have observed points x1 and y1, and you have x2 and y2, and you say x2, y2 observed versus predicted. And he draws a line through here, which is an okay fit for these lines, but clearly you have 2 lines. You could easily draw a line directly through them. And he draws it kind of skewed for a reason to make you actually realize that, okay, it's a good fit. How do we maximize that? How do we actually improve upon that? And here you see the basic line formula written more in the statistical format rather than the standard algebra format. So you'll know y equals mx plus b. This is y equals theta naught plus theta 1x. And you kind of swap the mx and the b, and mx becomes theta 1x, and b becomes theta naught. So going into a little bit more detail, you have what would be called features, x1, x2, and y observes, or the targets, or whatever you want to call it, which is y1 observed, y2 observed. Then you have your predictions, and your prediction is your model. And you have y prediction, y1 prediction, y2 prediction. And again, there's your linear format there. What I really liked about this post was this table here, or this tree diagram that he put. When I first saw it, I didn't quite get it because it's actually, in my opinion, turned upside down. But I spoke to Isaac about it, and actually the way he looks at it is actually, in my opinion, upside down. And it makes a lot of sense in that regard. So he starts at the end goal and then works his way back. I start with the starting steps and then would normally work my way down. So I'm going to work that way. But just note the reason for that is basically, here's your end goal. This is the main product, which is this J, and here's how you get it. So here we have our thetas. We have theta naught, theta 1, theta naught, theta 1. They're repeated. They're repeated because we have 2 points, x1 and x2. And basically what you're doing is you're going to input some values for these. They're totally random. Then you're going to move your way up. This value is multiplied by 1. This value gets multiplied by x, which is literally what this formula shows, right? Theta naught times 1. There's no 1 there because it's inherent. And then theta 1 times x1. Same thing over here, except you've substituted now for x2. The next step up, you move up the ladder. You're actually going to see, okay, how far is my prediction from my observed value? And you calculate that. That calculation is placed here. That's then squared. It's squared and then divided by 2. I honestly don't know why you're divided by 2, but that's convention, so we'll go with it. It's kind of, in my mind, a sum of squares, right? So you've basically taken 2 values, you've kind of inversely averaged them, kind of, in a square function, and you get this a value. The a value is combined with the other a value for the x2 and the y2, or the set first and second points, and then you combine them and sum them to get what's called J. J is your cost function, and cost function is going to be thought of as like sum of squares. You're trying to minimize this. Sum of squares, you're taking each point, you're taking the difference, and you're squaring it. Well, it could be sum of squares, and you're trying to tilt this line just so that sum is as small as possible. If you tilt it too much, you pass the minimum. If you don't tilt it enough, you haven't reached the minimum. So that's what we're aiming at. In order to do that, we're going to create what's called a path value. And you'll notice this path right here is x1, which is right here, multiplied by this piece right here, y1 predicted minus the observed. So what's the difference? Multiplied by 1, which is right here. Excuse me, I believe it's this one here. Then you're taking the other side, and you're doing x2 multiplied by the difference multiplied by 1, and you're adding those together. That's your path value, right? Well, we're going to take that path value and multiply it by what's called an alpha right there. The alpha is also called learning rate. The bigger a learning rate is, the bigger the step you'll take. So if you start with an original value for this theta of, let's say, 10, and my difference winds up being 8, and then I multiply it by a learning value of 10, well, I'm going to take an 80-step change, which doesn't really make sense because I could go in the wrong direction. I could overshoot it way too far. Or I could multiply it by 0.10 or 0.01. And that gives me a much smaller step as you go through it. So moving from the blog post, he's actually set up also this spreadsheet, which basically shows you each step along the way. And so each iteration going through here, he actually has graphs of each point. And then he sets a random theta value. He has his designated x and y, which is going to be 1 and 2 for 0.1, and it's going to be 2 and 8 for 0.2. And then you have what that predicts. And when you click on the cell, which is nice, you can actually see his calculations. So you can see that this predicted value is dependent on C3, which is your first assumed theta, times D3, which is your first x value, plus B3, which is going to be your y-intercept. So that gives you your predicted value. Here's the difference, and here's your A1. So all well and good, and it moves through. It just doesn't quite click for me when you put it in a spreadsheet. And you can see path values and the alphas that he used, and also alphas that he suggests trying. Okay, all's fine and great with that, but let's actually turn that into Python code real quick. So we have this set up, and again, here's his website if you want to check it out. I highly recommend it. He has a lot of posts up, and I'm working on getting through them. So this one's for gradient descent in linear regression. So we're going to load in NumPy and Pandas to start. NumPy is going to be used for array operations, and Pandas is going to be actually to store our data in a CSV-style tabular data set. Okay, so we have that set up. Now we're going to create our 2 points. We have our x's and we have our y's, and I've segmented out this way because we're going to segment them out. So the first point is 2 and 5. The second point is 12 and 18. So it's a little weird way to look at it, but that's how it's set up. So we have our x's and y's. And here again, to remind you, the goal is to minimize j. J is the cost function. So we're going to have to track it. And in order to track it, we have to store it somewhere, and then we're going to find what the minimum value is. So we create this gradient descent function, and we're going to use a random theta naught, a random theta 1, an alpha, which is our learning rate, which is actually, this is very sensitive to. So it's a little bit tricky, but you'll figure out what works best for you. We'll input our x's and our y's, and then we're going to select how many iterations we do. You could select a goal, which you may never arrive at, but number of iterations keeps your computer from freezing, and you can play with it a little bit. So the first step, we kind of hard code these aspects in. The first thing, we're going to figure out how many rows we want in our data set, and we're going to set it as float. We're setting it as float because when we put it in, we want decimals, because the slope is not necessarily an integer value, and it'll kind of mess with your output. So it's going to be the number of iterations. That's how many rows we're going to have. Then our data is going to have columns called iterations, and the values are going to be rows. So not very interesting, but it's going to go 0 to 99 or whatever value you put for iterations, but it's going to have values listed as names for columns. The reason we just have 0 through 99 is because we're going to override it. We just wanted to set the size for it. So we're going to make a data frame, and it's going to be pulled from this. So when we run that, then we're going to actually start iterating, and we're going to go through each one of these iterations. The first step, we're going to set the first row for the iteration column to the index. Iteration 0 is going to be iteration 0, iteration 1 is going to be iteration 1, and then we'll keep adding to that. The first theta is going to be whatever we put in. But you'll notice down here, we're going to update that. So the next iteration it will update, and that will be updated for the next row down. We're going to do the same thing for theta 1. So the first row is just whatever we put in. The second row is the updated one, the updated one, the updated one. Hopefully it's improving along the way. Then we're going to initialize a couple of parameters. One is just this y prediction variable, and it's going to be set to zeros, and it's going to have 2 pieces to it, so 2 zeros. Then we set temp, which is going to be another index, to 0. Now we're going to iterate through our x's, and we're going to try to figure out what the prediction for each of those values is. In order to do that, this is the line formula. So you basically have the y-intercept, the slope, and whatever x you're on, because we're iterating through them, and you're going to put that in at this y prediction at the value of the iteration you're on here, and then you're going to add 1 to that iteration, and you're going to do it again. So just for the 2 points we have, we're going to do it twice. Then you take the error for that, And the error is going to be fairly important. Again, the larger the error is, the worse off your fit is. The smaller it is, the better it is. Then we're going to calculate our A's, and if you remember, going back to Isaac's thing, the calculation of the A is here. It's 1/2 multiplied by the difference in the values squared. So we come back, 1/2 multiplied by the difference in the values for the first for the x1, for the x2, and we square each. So you get A1 and A2. Then we're going to set the value for the cost function at that index to the addition of those. And again, going back to Isaac's blog, right here, we're setting it to this value here. That's the first iteration. Then you go back through. So we calculate, or before you go back through, we calculate the path length, the path value, which is done right here. And we're going to do it for both theta naught and theta 1. And what we're going to do for theta naught is just take the error without any input values. Then we're going to take the error multiplied by the input values and add them together. So that gives us path 0, or it's going to be just the differences in the y errors. And then path 1 is going to be the differences in each error multiplied by its appropriate x value. Then we update our theta values. This is the last step to the puzzle. Last step to the iteration puzzle, I guess. The theta naught is going to be set to the path naught, path 0, multiplied by the alpha, taken away from the initial theta. So we've just basically decreased the theta value by that much, or increased it depending on what the difference was, positive or negative. Then we do the same thing for theta 1. And we start over. Theta 0 goes here, the theta 1 goes here, and we go down the list again. At the very end, we're going to figure out what's the minimum of the j column. What value is the smallest value we arrived at. And then we take that, and we take all the values from the DF, from the data frame at that index. And then we're going to return that. So let's go ahead and run this. Again, hopefully no errors. And now we're going to actually test it. So we're going to set number of iterations to 1,000. You can do it to whatever you want. The larger the value you have, probably the better you'll get. Would take longer, but probably the better you'll get. And then we're going to set theta naught to a random value between basically 0 and 10, and between 0 and 10 for theta 1 as well. And I'm setting the learning rate, or alpha, to 0.0015. I tried a few values, and depending on what you put, you could get awful answers. So test a few values out here. So after that, we'll run the function. We'll input our random theta, our other random theta, our alpha, our x's and y's, and our number of iterations, and we output it as best. Let's see how we do. And here's our best. So we did 0 to 999, so 1,000 iterations. The theta naught, which is our y-intercept, was set to 2.32. Theta 1 was set to 1.3. And our j, or our cost function, is quite small. We're almost at 0. We did pretty well. So next, let's actually test it. We have our values, but we have no clue if it's any at all accurate. Aside from this j value seems to be good. So what we actually want to do is make a prediction. We're going to input our model here, our gradient descent model. We'll call it a model. And then we're going to put in an x value, one x value. And we're going to return basically the prediction of that. This is going to be beta dot theta naught. And just to show you, let me put this in. So we can do beta dot. And if we do theta naught, just to show you what it looks like, did I do it? Oh, sorry, best dot theta naught. There we go. So we get this value right here. So 2 points. So what should come out is exactly that. And then when we add it here, we should get theta 1, and we should get the slope there. And then we're going to multiply it by x. So let's see how we do. And if I put in the value of 2, which was one of our initial points, 2, 5, we should get something close to 5. So let's see how we do. Up 4.93. Pretty close. Not bad. So then if we put in a value of 12, we should get something close to 18. Let's see how we do. 18.01. I think we did pretty good there. Just to test it finally, I'm going to do the basic y-intercept form. And I'm going to solve for the slope, I'm going to solve for the y-intercept, and then I'm going to see what it gives me as an output. This is kind of redundant, but I'm going to do it just for the sake of it. So I'm going to find m for the slope. which is the differences in the y's divided by the differences in the x's. Then I'm going to solve for the y-intercept, which these are the steps. You have y equals mx plus b, and then you take mx, flip it underneath y, or divide y by that, and you get b equals y over mx. So that is this, and excuse me, I totally did it wrong there. So it should be this. That's why I had that. So I subtract mx, not divide by, and then you're going to solve for b here, and then we're going to test it. And so we're actually going to plug in the value. So let's see what we get as an output, 5. So when we put in 2, which was this, xs at 0, again, xs at 0, we get 5. Our guess, our best estimation, again, going back, was 4.939. Pretty close. So hopefully this gives you a little bit of an understanding of what gradient descent is doing. It's basically doing what you would do by drawing your best fit line between points, except it has to do it in a way that our brain is not familiar. So basically it has to say, just draw a line anywhere, see what the difference is. Change it a little bit and see what the difference is. Change it a little bit and see what the difference is. And it keeps doing that until the difference is very, very, very small. And it may or may not arrive at exactly the right answer. Arguably, it would never arrive at the right answer because you have so many decimal places and it could be slightly wrong. But you should get it fairly close. And if you need to add more points to this, obviously it makes the line drawing more complicated. But you should be able to adapt the function appropriately so that you can actually add multiple points to this. And I may do another video on that in the future. Anyway, hope this was helpful. And again, check out this blog. It's fantastic, and it covers a lot of really useful points, both on the math side and the data science side.